in W, and also V in the orthogonal complement. And we know every vector in W is orthogonal to every vector in its orthogonal complement. So that we have this inner product to be 0, and so by negativity, this is the 0 vector. Okay, so that so we have this result. Now we will be able to describe theorem 7.1.15. Okay, so again, V is an inner product space. Maybe not finite dimensional. Right? So V can be finite dimensional or not finite dimensional, but W is a finite dimensional. Okay, so W must be a finite dimensional subspace of V. All right, so now for each vector in the inner product space V, there exists a unique, right, U in W and V in the orthogonal complement of W, such that the X is equal to U plus V. Right? So that every vector in the inner product space can be expressed as the sum of an element U in W and a vector V in the orthogonal complement of W. And this expression is unique. Okay, here is unique. Furthermore, we have the orthogonal complement of W is equal to W. Okay. So the proof. Now we let U to be the orthogonal projection of X onto subspace W. Okay, and we let V to be the difference of X and this orthogonal projection. Okay, right? So we have that. Then by the definition of orthogonal projection, we know that U is orthogonal to V. Okay, so okay, so we have so maybe I say, so we have so we have U is in W and U orthogonal to V. Okay. And this, which implies that V is in the orthogonal complement of okay. I have to say U is in W and U is in orthogonal to the whole maybe else. i.e. Okay, I forgot. V and maybe S. Which means that okay. So this is the from the definition of orthogonal projection that U should be in W, and also the difference should be orthogonal to every vector in W. So I use this V is orthogonal to W here, which means that this is, or if you like, you just say, okay, for that. All right, so that and this implies that V is in the orthogonal complement. Okay, the same is so we can have the decomposition with U in W and V in the complement. Okay, so now we have this decomposition first, but we have to show that this decomposition is unique, right? So assume X is equal to U prime plus V prime with U prime is in W and the V prime is in the orthogonal complement. So suppose we have another decomposition, U prime plus V prime. Then, all right, so then we have U plus V equal to X equal to U prime plus V prime. This implies that U minus U prime equal to V prime minus V. Okay, and so this is in the intersection of W and its orthogonal complement. Because that W and the orthogonal complement are subspaces. So U and U prime are in W, so their difference is in W. Okay, so this is in W. And the V prime and the V are in orthogonal complement of W, so their difference is also in the W perp here. And they are equal, so that they must be in here. But as we know, the intersection is just the set of the zero vector by lemma 7.1.c. Okay, so we have so that U minus U prime equal to V is equal to zero vector. So that this is okay. So the representation is unique. Right. The last thing is to show the orthogonal complement of the orthogonal complement of the W is equal to W itself. Right? Right? Since W orthogonal to X for all W in and right, so we know any vector in W and any vector x in the orthogonal complement of W are orthogonal to each other. Okay, so that we know x is in W, so that implies that is orthogonal to x for all. Okay, so if W is a vector in W, then W is orthogonal to every x in its orthogonal complement. But by definition, this says that W is in the orthogonal complement of the perp here. Okay, so that this vector is orthogonal to every vector in this subspace, so that this vector is in the orthogonal complement of this subspace here. All right, so we have the inclusion here. So W is a subset of this perp of the perp there. All right. Now to show the other direction, we let x in the perp of the perp. Okay. All right. Now they are, so by our previous decomposition, so they are U in W and the V in the perp, such that x is equal to this one. Okay, so we have this decomposition. Okay, but we know x will be orthogonal to V. Okay, because V is in the orthogonal complement in this set, and x is the orthogonal complement of this set. So x must orthogonal to V, and of course U is orthogonal to V too, right? Because U is in W, and V is in W perp. So U is orthogonal to V, right? So we have these two orthogonality. Okay, and this implies that 0 is equal to, okay, so because that they are orthogonal, so this inner product is equal to 0. Okay, now x is equal to U plus V. Okay, so by linearity, we have this sum. Again, U and the V are orthogonal, so this is 0 plus, so this is, so this is 0, right? So this implies that V is 0. So V is 0, and the x is equal to U, but U is in W, so that x is equal to U is in W. So every x in the perp of the perp implies that x is in W. So this implies that okay, so we prove this in equation and combine these two. We have the conclusion here. Questions? Any questions? Okay, good. All right. This property is a special case in the following definition. So a vector space V is called the direct sum of two subspaces W and U of V, and the notation is here denoted as V is the direct sum of, so the sum with a circle. If first V is the sum of X, W and U, okay? You know the meaning of the sum. Okay? And if you forget, then I will give you the idea. Just form the sum, and the W is from the capital W, and the vector U is from the capital U here. All right, so if V is the sum of these two subspaces, and the intersection of these two subspaces is the zero, is trivial. Okay, so this is the case, and in this case, in this case, there exists a unique. So in this case, for each X in the vector space, there exists a unique U. There exists a unique W and vector U in subspace U, such that X is equal to W plus U. Okay, so there exists a unique. Existence is from here already, right? But uniqueness is from the intersection of W and U is the trivial subspace. Okay, and the proof is similar to we have done here. Okay, just here, just like here. Okay, so theorem 7.1.15 says that an inner product space V is the direct sum of a finite dimensional subspace W and the orthogonal complement of W. Okay, of W, yeah. So up to now, we just show that W should be finite dimensional. Because if W is infinite dimensional, we don't know the answer yet. Okay. All right. So this section is to answer a question raised in 7.1 orthogonalization. Okay. Right, so we will demonstrate a couple of procedures to construct orthonormal basis to construct orthonormal basis for finite dimensional inner product space. Okay, because in the discussion of orthogonal projection, we rely on an orthonormal basis, right, to obtain orthogonal projections of a vector onto a finite dimensional subspace W, right? And so we have to answer the question: is there any orthonormal basis? And the answer is yes. Okay, so right. So the first one is the Graham-Shimmits process. Okay, so first of all, we have suppose we have a linearly independent set. Okay, so this linear independent set has m vectors. Okay, u1, u2 up to um. All right, and we let wi to be the span of u1, u2 up to ui. Okay, for all from M. Okay, so we will construct the subspace using the basis vector, using the vectors in this linearly independent set. So we have a chain of we define W0 to be trivial, and so it will contain in the 1, 2, m, and this one is the span of S. Okay. So Wm is the span of X here. And from here, the dimension, so you can see the dimension of Wi is equal to I. Okay, so you know, so the dimension of this subspace increasing sequence of subspace. Okay, so we have increasing sequence subs become bigger and bigger. Okay, here. All right, and we also, for convenience, we define projection of the W0 defined to be the 0 vector, okay, for all. So that is because the W0 is the trivial subspace. So we just define, this is just define a definition, right, for convenience. Okay, so we will, so we want to obtain and also normal set called Q1, Q2 up to Qm. Okay, so we want to obtain an orthonormal set such that the Wm, as we know, is the span of X is equal to the span of Q. Right? So I think a procedure to obtain, right, is as follows. Step 1, we obtain the first vector in this orthonormal set Q1, right, to be, first of all, is use U1, right? So we use the U1, the first vector in the S set, minus the projection of U1 to W0. Okay, and normalize it. But this is just U1, okay? Because that the projection is 0. Okay. And I write down this because of to demonstrate the procedure in a certain symmetric way. Okay, and so you can see that Q1 is an also normal set, and and also normal basis for W1. Remember, W1 has a basis which is U1. Okay, so but the U1 and the Q1 just are proportional, linearly related to each other, because Q1 is the normalized version of U1. Okay, so now we construct also normal basis for W1. Okay, this is the first. And how about step 2? Okay, the step 2 that we construct Q2 that using U2, all right? And then we project, we subject the its project or some projection to W1, okay? And so we do the normalization. Right, so we eliminate the component which projected to W1. Okay. All right, and this we know is equal to U2 Q1. Okay, because Q1 is an orthonormal basis for W1. All right, so the projection is equal to to this vector. Okay. Now, okay, so we will see that since U2 is not in W1, because if U2 is in W1, then U1, U2 are linearly dependent. This is a contradiction, right? So this is not in W1, so that U2 minus the projection of U2 to W1 is a non-zero vector. Okay, and this non-zero vector in what? In W2 intersect W1 perp. First of all, this vector is in W1 perp, of course, because that this is the orthogonal projection of U2, right? So as we know, here, this is U2, this is W1, and here, this is the projection of U2 onto W1, and so we have orthogonality. This is U2 minus projection of W1 U2. So the difference, that U2 minus the projection, which is of course non-zero because U2 is not in the W1, and so maybe I will right here. All right, so it's in W1 perp. But this one is in U2. I'm sorry, it's in W1. In W1. And the W1 is a subspace of W2. Okay, in here, subspace of W2. All right, and the U2 is also in W2. So it's a linear combination of vectors in W2. So that is in W2. Okay? So that this vector is in the intersection of W2 and the perp of W1. Okay. It's crucial to know this. So do you have any questions about this fact? So it's non-zero, so that's why we can normalize it, okay? This is the reason why we can normalize it. So it's non-zero, and also it's in the intersection of W2 and W1 perp. All right? Okay, so Q2 is a normalized vector in W2, and Q2 orthogonal to Q1. Okay, because Q2 is a normalized vector of this difference. All right, and also this one is in W1 perp, so Q2 will orthogonal to Q1 because Q1 is in W1. So Q2 is a normalized vector in W2 and Q2 orthogonal to Q1. Okay, so that Q1, Q2 is an also normal basis for W2 since dimension of W2 is 2. Okay? And also normality implies that this set is linearly independent. Right? So this is implies and by theorem 7.1.2 and the theorem 5.2.10. Okay. Theorem 7.1.2 says that this also normal set is linearly independent. Now we have a linear independent set of size 2. And 2 is equal to the dimension of W2. So by theorem 5.2.10 says that such a linear independent set must be a basis. All right. So the conclusion is that Q1, Q2 form an orthonormal basis for W2. Okay. Right. So we are one step closer to our goal. So we find an orthonormal basis for W1. We find an orthonormal basis for W2. And we were doing the same procedure furthermore up to this one. Okay? So that so suppose that we have keep doing things, and in step K, suppose in step K we already have QK, and the QK is actually UK minus the projection of UK onto WK minus 1. Okay. By using the previous subspace WK minus 1. And then we normalize it. All right, and because we already find an orthonormal basis for W sub K minus 1, so this is actually equal to UK Okay, so we obtain QK, and we obtain that Q1, Q2, QK is an orthonormal basis for WK. All right, suppose we have the data. So you think about K as 1. Think about K as 1 here. Okay, we already. And now we go to step K plus 1. In this one, now since U sub K plus 1 is not in WK, right? So the U sub K plus 1 minus its orthogonal projection onto WK. Right, so this difference is non-zero. So it's a non-zero vector in W, k plus 1 intersect the orthogonal complement of Wk. Okay? So this is important to know that this is non-zero and it's in here. All right? And because it's non-zero, so we normalize it. We let Q, k plus 1, to be to normalize the version of this vector. Okay, so we know that. All right, and because that Wk has an orthonormal basis, Q1, Q2 up to Qk, so we know this is U k plus 1 minus UK plus 1, Q1 minus UK plus 1, QK, and UK plus 1 minus UK plus 1, Q1 minus UK plus 1. Okay, so now we have QK. All right, so then Q k plus 1 is a normalized vector in W k plus 1, and Q k plus 1 orthogonal to Qi for all I from 1 to k. Okay? Because Q sub k plus 1 is now in the perp of Wk. Okay, so they orthogonal to them. So that's Q1, Q2 up to Qk plus 1 is an orthonormal set. For it's also normal basis for Wk plus 1. Okay, so Wk plus 1. So now we finish the k plus 1 step. Okay, and we'll keep going on. So actually you can see that now we have a recursion, right? Or you can by induction. So you can go on. So finally, at step M, at step M we have Qm, which is Um minus the projection of Wm minus 1, Um, so which is Um minus Q1 Qm minus 1 Qm minus 1 here, Q1 minus Qm minus 1, Qm minus 1. Okay. And finally, Q1, Q2, up to Qm minus 1, Qm is an also normal basis for the M, and which is the span of S. And we have done. So this is the end of the procedure. Okay? And this procedure is called, so this procedure is called the Schmitt's. Sometimes we put also gonalization process. Okay, so basically, so we describe the Schmitt's orthogonalization process and also prove that it works. Okay, we prove that it works. And so now we can state our theorem 7.2.1. Every finite dimensional inner product space okay, has an also normal basis. Okay, and the proof is simple because the Schmitt's process can be applied to any basis. All right, for a finite dimensional inner product space. Okay, so once we apply this process to a basis, then the ending point we have an also normal basis. Okay. Okay, and if we look at the process, we know in every step we have to normalize the vector. Okay, and so if you do hand calculation, usually you will involve in the square root of something. Okay, and you have to carry on all the square roots further, right? So it's cumbersome. if you do the process by hand. Of course, if you do the process by using MATLAB or you just write the code in C, C++, or in Python, then computer will do it for you. Okay, so that's fine. You don't need to worry about it. But if you, for example, in examination or in sometimes in person discussions, that to do the normalization, that would be I think painful. I mean, at least for myself. Okay, so that here is another version that presented is called unnormalized. The Schmitt's. It's a variant of the Schmitt's process. We call unnormalized. But actually, so the procedure is that to obtain, and also normal, the idea is here, from a basis, all right, is equivalent to obtain an orthogonal basis from a basis first, and then to normalize each vector in the orthogonal basis. So that would be easier because the last step we just do a normalization. Okay. So in during the modified process, we don't need to worry about the square root. That would be lighter for us to do the process by hand. Okay. But before that, we need a theorem. Okay. So let's suppose we have Z1, Z2 up to Zk. So, all right, I think to save my time, I just say that an orthogonal basis for a subspace W of an inner product space V. Right? Then for all x in V, the orthogonal projection, okay, the orthogonal projection of x onto W, okay, can be computed component-wisely. First, you project x to every directions in this orthogonal basis, and you sum them up together. Okay, so you can do that, right? One by one, etc. So you can do that. Okay, and you know how to do the projection to every basis vector. So we know that this is the I here. So you can see that the projection here involve only inner product, and you do not need to do any squaring, right? Because doing inner product in many situations is much more easier, right? Just some algebraic manipulations. Okay. So that there is no square root involved here. Just inner product be involved. Okay. All right, and the proof is here. All right, so we know the orthogonal projection of x onto W must be in W by definition, right? So we have that the projection is alpha 1 Z1 plus alpha 2 Z2 plus plus alpha k Zk. Okay. Okay. So we must find the coefficients. Okay, so we must find the coefficient. Okay, now since x minus this projection is orthogonal to, so it's in the orthogonal complement. So we have that x minus projection with zj must be 0 for all with k here. And so that summation alpha I, the I from 1 to k, is j. Okay, and this implies that k so this implies that x zj is equal to the summation okay, but this is equal to but zi's are orthogonal to each other. So if I not equal to j, this interval is 0. Okay, so this is equal to alpha j and zj. Okay, so that means that alpha j x zj. EJ. Okay, and we have done. So this is the situation we have. All right. So now, so a modified grand Shimmits process is as follows. Step 1, we let Z1 equal to U1. Okay, and so this is the U1 minus the projection of W0 U1. Oh, so we just U1 minus the projection of W0 U1, and this is U1. Okay, and so basically Z1 is U1. So Z1 is an orthogonal basis for W1. Okay, so now we find an orthogonal basis for W1. Without normalization, we only get an orthogonal basis. Okay, and step 2. The step 2, the Z2 is U2 minus the projection of U2 onto W1. Okay, and this is U2 minus U2 Z1, 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 and Z1. Okay. Now, since U2 is not in W1, we know U2 minus projection of W1, U2, okay, is a non-zero vector in W2 intersect with W1 perp. Okay. So the reasoning is the same as in our original procedure. All right, so that Z2 is a non-zero vector in W2, and Z2 is orthogonal to Z1. Okay, so this implies that Z1, Z2 is an orthogonal basis for W2. All right, again, by theorem 7.1.2. 7.1.2 says that a orthogonal set implies linearly independent set. And also by theorem 5.2.10. Because this is a linear independent set of size 2. And the dimension of W2 is 2. So they are the same, right? And so this linear independent set becomes to a basis. Okay, so we have done for the same step. And similarly, in step K, suppose we are in the step K, and so ZK is obtained from UK by taking the difference of UK and its projection onto W sub K minus 1. Okay? So from our previous lemma, this orthogonal projection is equal to this linear combination. All right, and suppose Z1, Z2 up to ZK is an orthogonal basis for WK. All right, so now we go to step K plus 1. Again, ZK plus 1 is not in the WK, right? Because that, so U sub K plus 1 minus the projection or orthogonal projection of UK plus 1 onto WK is a non-zero vector in WK plus 1 intersects WK perp. All right, and so we let Z, oh, I'm sorry, U is UK, sorry. So we define ZK plus 1 to be UK plus 1 minus this projection and which we know is equal to equal to the, this vector. So we can, with that Z sub K come to here. So okay. So that Z K sub 1 is a non-zero vector in wk plus 1, and this sub k plus 1 is orthogonal to zi for I from 1 to k. Okay. This is because that z sub k plus 1 is in the orthogonal complement of w sub k. And so that z1, z2 up to zk plus 1 is an orthogonal basis for wk plus 1. Again, by theorem 7.1.2 and the theorem 5.2.10. Okay, and so we keep going on to step m. So we have for z m, it's the um minus the projection of um up to onto w sub m minus 1, and this is um is the vector, and also we have z1, z2 up to zm, and it's an orthogonal basis for wm, and this is the span of x here. Now, to obtain an orthonormal basis, we have the one more step. So the one more step is that the qi to normalize the zi for all I from 1 to m. And in this case, q1, q2 up to qm is an orthonormal basis for wm. Okay, and we have done. Okay, so I presented two procedures to obtain an orthonormal basis for a finite dimensional inner product space. Okay, from a basis, from arbitrary basis to that. Okay, all right, and so I'll stop here, and as I sent you a notice that I will prepare a recorded lecture for you, so that I will finish the last part of the chapter 7 and give a fundamental material about chapter 8, because chapter 8 is very diverse, and the material in chapter 8 has a lot of applications in different branches. So I would like to lay you down on a solid background. And so in this additional lecture, recorded on Friday, I think I will access that, maybe before Friday, okay? So that you have to study this lecture, such that you are able to work on the next recommended homework exercise, as well as to prepare I think that would be the last quiz, I think so, after the new year. Okay, so all right, so anyway, wish you a happy new year. Okay, I'll stop here.